Check it out now, y'all.
nanoHUB-U, online instruction.
Okay, welcome to week 3. Let's get started. So we're trying to understand the current voltage characteristics of nanoscale MOSFETs. Current is the product of charge times velocity. We spent last week looking in some detail at MOS electrostatics and charge. Our focus this week and for next week is on carrier transport. So the velocity is determined by how charge flows across that barrier. We're going to begin to look at that problem this week. Now the first lecture gets a little bit mathematical. I'll introduce an approach which, if you've taken Professor Datta's course or read his books, will be very familiar to you, but many of you may be seeing it for the first time. The first lecture will look a little bit mathematical, but we'll spend the rest of the week getting comfortable with it and understanding physically what these terms are all about. So let's dive into things. Now, if we were talking about transport, and if you come to this field with a traditional background in electrical engineering, you probably started with the drift-diffusion equation. This looks very physical. Carriers drift in an electric field, or they diffuse down concentration gradients. If we do this in 2 dimensions, the units of current density are amps per meter or amps per centimeter. This looks very physical, but it really breaks down when we get to the very small, short channel types of devices that we're going to be talking about today. It's really only valid for diffusive transport when the device is many mean-free paths long. We're going to introduce a new approach called the Landauer Approach. Actually, it's not so new. It's been around quite a long time. But it's a very physically sound and relatively simple way to look at transport in small devices. So we'll ask, what is the current through a small nano device? And we'll develop a simple expression that contains some fundamental constants, a parameter we'll call transmission that we'll physically interpret and get comfortable with, a parameter that we'll call the number of channels or modes that we'll get comfortable with, and the difference between the Fermi functions or Fermi levels of the 2 contacts. So our goal today is to derive this equation, and our goal for the rest of the week is to begin understanding it more deeply and using it and applying it to MOSFETs. So there are 2 questions that we want to focus on today. How is the number of electrons in that small device related to the Fermi levels in the 2 contacts and the density of states of the device? And how is electron current related to those same parameters? Okay, so I'm going to be using a version of this Landauer approach that's due to my colleague Cipriano Datta. And the approach works this way. We'll think about our device as being described by some density of states. There's also a potential energy that might be controlled by a gate. So this might be a small chunk of silicon with a density of states of silicon. It might be a small molecule with some energy levels of the molecule. Whatever it is, it has some density of states. We need contacts to make a device. We're going to think of these contacts as large thermal equilibrium reservoirs. That means that each one is described by a Fermi function and an equilibrium Fermi level. The difference, though, is that out of equilibrium, the Fermi level in contact 1 may be different from the Fermi level in contact 2, because if we apply a voltage to contact 2, we lower the Fermi level in contact 2. But we're assuming that the current flow is relatively small compared to the large size of these devices, and strong scattering maintains equilibrium in those 2 contacts. We need to specify how the contacts are connected to the device. The easiest way to do that is in terms of these characteristic times. So these times tell us how long it takes to get charge in and out of the device. So if we have a charge in a device, tau 1 is the time it takes to escape into contact 1, tau 2 into contact 2. And we may have a gate voltage that changes the electrostatic potential energy and moves those states up and down, and then we have a transistor. And we will be interested in determining how many electrons are in that device and what current flows through that device. Now, I'll just point out for later that if our x-axis points to the right, we've defined positive current flowing into contact 2. We've defined that to be positive, so a positive current flows in the negative x direction, and that's something we'll have to keep in mind from time to time. Now, there are some assumptions, but these assumptions are typically rather well approximated. What are the assumptions? Well, I'm going to describe the device by some band structure, E of K. That's not a necessary assumption. If we had a small molecule there, we wouldn't have a band structure. And for that more general treatment, I'll refer you to Professor Datta's books and nanoHUB-U course. The contacts are assumed to be large, to have strong inelastic scattering, to always be very close to thermal equilibrium. That's an assumption. Somewhere there's a contact. We may have to go out a ways. There may be a large metal contact and a big wire, but somewhere there's a thermal equilibrium reservoir that we will define to be our contact. The self-consistent potential U here that we control with the gate is the average electrostatic potential that the electrons feel due to the other electrons and to the applied voltage. Now, that's an approximation. It's called the mean field approximation, that we can think of each electron experiencing the average potential of all of the other electrons. It misses some things, especially when there is so-called strongly correlated transport, and we get things like single electron charging. That's beyond the scope of this course, and again, I'll refer you to Professor Datta's nanoHUB-U course, where those kinds of effects are discussed in more detail. We're going to assume that all inelastic scattering, that is scattering that changes the energy of an electron, takes place in these two contacts, not in the device itself. That means that electrons flow in independent energy channels across the device and only change their energy when they enter the contact. And the final assumption is that the contacts are perfectly absorbing or reflectionless. An electron that goes into the contact doesn't reflect and return to the device. It's thermalized and comes to thermal equilibrium in that contact. Okay, so now let's go step by step and see if we can derive an expression for what goes on in this device. I'm going to ignore the electrostatics for now. Let me consider the case when I only have one contact connected to the device. That's not a very interesting device. No current is going to flow in steady state. But you can see what will happen. This contact will try to fill up the states in the device according to its Fermi level and bring everything to equilibrium. There will be an initial transient, and then we'll end up with an equilibrium number of electrons at some particular energy that is the density of states in the device times the Fermi function of contact 1, which is filling those states. I could write a simple little equation that tells me what the transient flow is, either in or out, to establish that equilibrium. And the equation looks like this. It's the equilibrium number minus the number that are already there. So if the device is empty to begin with, there's a positive flow into the device. The characteristic time here is tau 1 at connection to the device. So this gives me the rate that electrons either go in or out until things settle down and thermal equilibrium is established and we get the equilibrium number of electrons in the device. I'll just mention, there's a factor of 2 that's included in the densities of states in everything that I do, depending on whose book you look at and whose notes. Some people use that included in the density of states and some don't. I will. Okay, we could do exactly the same thing with contact 2. Contact 2 wants to fill up the device according to its Fermi level, and after an initial transient, it'll do that, and we can write this simple equation for the flow F2 of electrons either into or out of the device to try to establish those equilibrium conditions. All right, we're going to be interested in steady state conditions because these transients are very fast. It's capacitances and parasitic effects that determine the response time, not the intrinsic transport phenomenon. So we'll be looking at steady state conditions. Now, the mental picture that we have here is that contact 1 is trying to fill up this device according to its Fermi level. Contact 2 is trying to fill up the same device according to its Fermi level. If we've applied a voltage, we have 2 different Fermi levels, and those 2 contacts can't be happy at the same time. Under steady state conditions, we can't have a positive flow in from both contacts, or the electron number would just build up continually with time. So under steady state conditions, F1 plus F2 must be 0. Means one of them must be negative. One contact must be continually putting electrons in, and another contact is continually pulling them out, and steady state conditions then are maintained. So if I want to know the current, it's just Q times the flow in from contact 1, or minus Q times the flow in from contact 2, according to the sign conventions that we're using here. Okay, so now we can compute the electron number relatively easily. We take this steady state condition. We have simple expressions for those two flows. We set it equal to 0, and we solve for the number of electrons in the device. And this is the answer that we get, making the simplification that the two contacts are the same, so tau 1 is equal to tau 2. If I want all of the electrons in the device, I need to integrate over all of the electron channels, and then this is my final expression for the number of electrons in the device. Now, that's relatively simple. In fact, it looks familiar. In equilibrium, you're probably used to calculating the electron density as the integral of the density of states times the Fermi function. This is the way we relate electron densities to Fermi levels in bulk semiconductors, in equilibrium. So we have something that looks very much like the equilibrium relation. The only difference is that we have two contacts, and we may have a voltage applied, so we may have two different Fermi levels. And this just says that half the states are filled by contact 1, and half the states are filled by contact 2. Okay, so we started with two questions, and we're making progress on the first. I just want to point out that I'm dealing with the number of electrons, not the electron density, so that the equations work in 1D, 2D, and 3D. You know, in the end, we'll want to discuss electron densities, the number per unit length in 1D, the number per unit area in 2D, or the number per unit volume in 3D. The density of states that I've been talking about is the total density of states per joule in energy range. So it's proportional to the length in 1D, to the area in 2D, and to the volume in 3D. Usually when we derive expressions for densities of states, we do it in, say in 3D, we do the density of states per unit volume per joule. I'll call that D sub 3D. And then we multiply by the volume to get the total density of states. So when you see a subscript here, D sub 2D means that I'm talking about the density of states per joule per centimeter squared. Just some notation that we have to keep straight. Okay, so we had these two questions. We've answered the first question, and now we can answer the second question. Let's look at the current. So we go back to our expressions. We had simple expressions for the flows in from contacts 1 and contact 2. The first equation gave us the number of electrons in the device. Now we simply multiply Q times the flow from contact 1, or minus Q times the flow of contact 2, and we have our answer for the current. So if you do that, I'll leave out the details. It's relatively straightforward. This is the result that we get. Some fundamental constants. I'm integrating over all of the energy channels so that I get the total current. A parameter gamma pi, half the density of states, times F1 minus F2. You know, what's this gamma? It's just a definition. It's h bar over that characteristic time that describes the rate at which we can get charge in and out of the device. So, you know, this will look a little bit to you like a uncertainty relation. Delta E, delta T is equal to tau. So gamma has the units of energy. Note that current doesn't flow unless there is a difference in Fermi functions. If the two Fermi levels are the same, then the two contacts are both trying to fill the device up to the same level. There is no net flow of current. It's only when I apply a voltage, change the Fermi level on one of the contacts, that current flows. So current is driven by F1 minus F2. Okay, so that answers the second question. I've drawn a dotted line. Remember, a red box is an important equation. I've drawn a dotted line around this box because we're going to want to take this equation and rewrite it in a different form. In that form, it's the same equation, just re-expressed in a different way, and we're going to be using this equation in a different form for the remainder of the course. Okay, so let's look at these three terms here. It's a little hard to see what their physical significance is. That's why we want to rewrite that term in something that we can make more sense of. This parameter gamma is h bar over tau. For tau is the escape time from the contact if the contact is bad. If the contact is good, it's just the time it takes for charge to flow across the device, or the transit time, because the contact then doesn't limit charge getting in and out of the device. It's just the flow across the device that limits it. Physically, the way we would interpret gamma, we call it the broadening, is to think about it if we had a molecule as a device. If we attached it to these electrodes and connect it to the outside world, the discrete molecular levels would broaden, and the amount of broadening would be given by this parameter gamma. Okay, for a good device, then the parameter tau is, for a good contact, the parameter tau is the transit time across the device, the length of the device, divided by the average velocity in the direction of transport. If we're ballistic. If we're diffusive, you might remember from random walk theory or the transit time of a bipolar transistor that the time it takes for carriers to diffuse across a region isn't proportional to the length of the region, it's proportional to the length squared. And the transit time in the diffusive case is length squared over 2 times the diffusion coefficient. So those are two limiting conditions. Okay, now if we look at this, we're going to try to interpret what this is. Gamma has the units of energy. Pi doesn't have any units. Density of states has the units of 1 over energy. So this is some number. And, what is this number? What does it mean? Well, we have expressions for everything here. We can plug them in, and we'll get an expression for that number. It's just Planck's constant divided by 4, average velocity in the direction of transport, density of states per unit area and energy, times width of the conductor in 2D. We're going to call that M, that number M. And we're going to see that it is the number of channels available for conduction at that particular energy. It's not obvious in looking at that equation what it is, but we'll be discussing that and trying to provide some physical insight in the next lecture. So that's what the number is. It's the number of channels at that particular energy. Okay, what happens when we do diffusive transport? Well, the only thing that changes is this transit time, this characteristic time for getting charge in and out of the device. So that's all we have to change. Instead of h bar over tau ballistic, we have h bar over tau diffusive. Well, I could multiply by tau ballistic and divide by tau ballistic. Why do I do that? Because if I do that, I recognize that this is what we had in the first case. That's what we called the number of channels M. So I can write this set of parameters as the ratio of the ballistic to diffusive transit times the number of channels at energy E. We're going to define the ratio of those 2 times as the transmission. It's a number between 0 and 1. Its physical interpretation is the probability that if an electron comes in from contact 1, it transmits across and goes out contact 2, or vice versa. We'll spend a lot more time later in the course getting familiar and understanding that physical significance. But we have expressions for both of those transit times. If I also bring in an expression for the diffusion coefficient that we will talk about later, but the diffusion coefficient is related to the average velocity in the direction of transport, the mean free path or distance between scattering events divided by 2, then I can express my transmission in a very simple form. The transmission in the diffusive limit is just the mean free path divided by the length of the device. And in the diffusive limit, that is very much less than 1. Okay, so let's recap. We've done a little bit of algebra here. We've taken our expression that was straightforward to derive, and we've just rewritten it. So current is related to transmission times number of channels driven by differences between Fermi functions of the 2 contacts, and we have an integral to evaluate to get the total current. The key parameters are the number of channels. So we have a prescription. We can calculate them for any band structure. We still need to do some work on the physical significance and understand it. I'm going to use this expression for the transmission. You'll note that when the device is very much less than the mean free path, the transmission is 1. That's the proper value in the ballistic limit. And you'll note that when the device is very much longer than a mean free path, the transmission is mean free path divided by length, which is the correct result in the diffusive limit. We will derive this result later and show that this result works in both limits and in between. So it gives us a way to describe quasi-ballistic transport where a lot of devices operate these days. Okay, a few more things. As I said, we're setting up the formalism, and then for the rest of the week we're going to be understanding this in more detail and applying it. This equation works for large bias or small bias, but I can simplify it for small bias, and that's frequently done, and it's an important result that you should see. So we're simply going to linearize. Under small bias, F1 is close to F2. We're just going to linearize that, and we'll see it's proportional to voltage. So it goes this way. We have this F1 minus F2, but they're close to each other because we're applying only a small voltage. That means I could take a Taylor series expansion for F2, and I could expand it in terms of F1, derivative of F1 with respect to the Fermi level, because it's only the Fermi levels that have been changed by that small applied voltage, times the change in Fermi level. So that's F1 plus dF1 derivative with respect to the Fermi level, and the change in Fermi level is just minus Q times the voltage applied to contact 2. So F1 minus F2 is given by this expression. If you look at the Fermi function, energy and Fermi level come in the same way. There's just a sign change. So I can also write that as minus dF1 dE times Q times voltage. So here's my final expression when a small bias is applied, and we'll use this frequently. The current is related to some fundamental constants. What's important now is the derivative of the equilibrium Fermi level. F1 is approximately equal to F2, and both are very close to the equilibrium Fermi level. So it's that derivative that will be important, and then we have a times voltage. So current is something times voltage. That something is what we call conductance. So we have an expression for the conductance. Now, in the final step, what I want to do here, just as we conclude, is to relate this approach, which looks much different from the drift diffusion equation that we started with in the slide number 2. I want to relate it to bulk transport in a long sample for which contacts don't matter. Then we should get the drift diffusion equation, although it might not be obvious yet. So for a long sample, I apply a small voltage. I'll have a constant electric field. The conduction band will just have a constant slope across the device. If the electron density is constant everywhere, then I'll have a quasi-Fermi level. That is, its separation between the conduction band is constant because the electron density is constant. And that's what my energy band diagram would look like for a very long resistor. If I apply a small bias to that very long resistor, I'm near equilibrium everywhere. So let me conceptually do something. Let me just define this region that's near equilibrium as contact 2, this region that's near equilibrium as contact 1, and I'll separate them by a long distance that's many mean free paths long, and now I've got a conceptual device that I can apply my Landauer theory to. Okay. I'll take the Fermi level of contact 1 as the quasi-Fermi level at this location. I'll take the Fermi level at contact 2 as the quasi-Fermi level at that location. So there's a change in quasi-Fermi level that's proportional to the gradient of the quasi-Fermi level. Okay, so if we want to analyze this device, we can apply our Landauer expression. We can use the transmission in the diffusive limit because this is a long diffusive sample. I can calculate the current density. Now we should define current density as positive in the plus x direction, so I'll count for that sign change. And I can use my Taylor series expansion for F1 minus F2 because I'm assuming a small bias. When you do that, we'll get an expression for the electron current density that will look like this. This lambda comes from the transmission. We have a number of modes per unit width there, and we have a change in quasi-Fermi level divided by the length. So that's our expression for the current. We can rewrite it. That change in quasi-Fermi level divided by length is just the derivative of the quasi-Fermi level. If I write it this way, then all of the constants out front are just the conductivity. So this is a very fundamental description of near equilibrium transport. Many books would start with this equation. You sometimes derive it from non-equilibrium thermodynamics. It comes out of our Landauer approach if we assume near equilibrium conditions. Now, if I make some additional assumptions, if I relate the carrier density to the quasi-Fermi level, solve for the quasi-Fermi level, take its gradient, express my conductivity as the product of the carrier density times charge times mobility, then you can just transform this fundamental equation into something that looks even more familiar, to our drift diffusion equation. And the relation between D and mu is just given by the well-known Einstein relation. So you can see that this Landauer approach, even though it looks much, much different, really reduces to conventional transport formulations like the drift diffusion equation for long samples that are in the diffusive limit. Okay, so I would think about this Landauer approach as the drift diffusion equation of the 21st century. This is really the place that it makes most sense to start at when you talk about transport, because you can always simplify it to the drift diffusion equation for big devices, but it applies to ballistic devices and small devices equally well. So we've developed the mathematics of this expression. If this is the first time you're seeing it, you're probably not completely comfortable with it yet, and you shouldn't be, but we're going to be applying it in the next lecture. We'll be comparing it to some experimental data, and as we use this for the rest of the course, you'll get more and more comfortable, and this will make more and more sense to you. We can simplify this same expression under low bias. Under low bias, current is proportional to voltage, and the constant of proportionality is the conductance, and then what's important is the derivative of the Fermi function. Okay, so that's the mathematical formalism. We've covered a lot in this lecture, but in the next lecture, we'll start with this formalism, and we'll begin to apply it and see that it can be applied to some real experiments and give us some very interesting insights into transport. So I'll see you for lecture 2.